All right, welcome back. In this video, we're going to be continuing our discussion of connections. Previously, we've talked about bolts and mechanical fasteners, connections and calculations that AISC requires as part of that study. But in this one, we're going to shift our attention to a different type of connection, and that's the connection type called welding. Welding is basically a process of joining two metal pieces together by heating the pieces to a plastic or fluid state. This is accomplished by heating an electrode that melts both the electrode and what we call the base metal or the connecting metal, and then it becomes liquid and then it fuses itself together as it starts to cool. Okay, there are lots of different processes of welding. We'll talk about a couple of them, but for our study, we're not going to be too concerned about this in as much as we're going to be looking at how to calculate the strength, capacity for our connection that way. All right. So most of the welding that we look at in our conversation consists of what we call arc welding. Okay, and the major processes that we have, and we'll go through these fairly quickly. The major processes are the SMAW method, which stands for shielded metal arc welding. Okay, sometimes affectionately called as stick welding. Okay, this is one of the oldest types of welding where I take an electrode, and I hold it with, with a clamp that allows a current to come through it, and then when I make contact with the metal, it completes a circuit that melts that metal and kind of fills the hole and melts the surrounding base metal at the same time. Okay, it's also very common in stud welding that is used in composite construction. The next one is the SAW method, which is a submerged arc welding. And then another one is called a GMAW, which is kind of a gas metal arc welding. Now, the basic premise of welding can be kind of depicted by this crude picture here, right? Okay, I've got two plates that I'm looking to fuse together. This will be kind of a groove weld, that there's a notch that's been prepared at that location. And then the electrode comes in, and basically I have a current source that this is hooked up to a power source that is then forms a current with the base metal. So there's a clamp that's put on this metal that returns back to the power source to complete the circuit. And when I touch this to the metal, it completes the circuit. And when the current flows, it basically heats up the end of this electrode. Okay, and when it liquefies, it falls into the opening and then it melts the surrounding area and then fuses with it as it starts to cool. Okay, now the terms that you'll see used in here and as part of the strength calculations, you'll always be looking at the electrode, which is this piece of it, as well as the base metal, which is the item that you're testing. Okay, now typically I'm welding two plates to each other, so when you do a base metal check, you have to check both sides. Okay, because one could fail before the other based on the calculations that we'll kind of go through here in a second. Okay, but that's kind of the general process of it. Electrodes themselves have strength characteristics just like the base metals does. Base metal will be your A36 or A992 or whatever grade of metal that you're working with. But electrodes also have a designator. Okay, and the most common by far is what we call an E70XX electrode. This has a weld strength of 70 KSI. Now, if you compare that to the metals that are 36 and 50 typically for FY, you can see that it's significantly larger, and it has to be because the area associated with the weld is much smaller than the area associated with the base metal usually. Okay, so I need a higher strength to be able to transmit the load through this particular connection. Maybe this connection is a tension connection where I'm pulling this way and I'm pulling on the other side on that, and I need to be able to transmit that force from the plate into the weld into the other plate. Okay, but by far the E70 is the most common of the bunch. Okay, sometimes you'll see an E60, and in that case he's a 60 KSI. So you can see that in these electrode designators is the actual strength of the electrode itself. So 70 KSI for E70 and 60 KSI for E60 is what we're looking at there. Okay, now there are a lot of variety of different types of welds. Okay, we're going to kind of focus mainly on the fillet welds, but I'm also going to kind of mention the groove welds just so you kind of have some exposure to it. So as we said, the first type of weld is called the groove weld. Okay, and this is an interior weld in that I have a plate that's here and a gap, and then a plate that's here, and I basically fill the gap with the weld metal to complete the connection. Now, if these have some issues and are the source of a lot of the minimum thickness requirements for this, because if this distance becomes too far and I try to fill it in, there's the potential possibility that this weld, as it's flowing into this area, that it cools and it stops and it never reaches the bottom. Okay, so we've got to have real good high quality assurance of the quality of the weld that we're getting, because I'm counting on this entire area to transmit through here, but if I get shortchanged on this, and I have some sort of gap there, then that's a significant reduction in this. And the fact that it's an interior weld means that generally these things are laid down such that, if this is my, it's constructed in a flat situation, right? That this is some sort of table surface or something, and that I have no way of inspecting the backside until I pick the piece up and literally flip it over, which is, in a fabrication shop can be a significant issue to be able to do that. And if it's in the field, you might not be able to do it at all if this is a plate that's up against something else. So it's there are some issues with groove welds. Now they're very good if they're done right and you have ways of assuring the quality of them. But these interior welds, you've got to be kind of careful of some of the problems with it. Right now, the fillet welds are probably the most common, and these are the easiest of the welds to make. Okay, and these are usually the cheapest to do and the easiest for that. And these are what is known as an exterior weld. And basically, what happens is you take two plates, and you're able to construct a weld such that it connects both plates on the outside. I mean, my electrode comes in and it just deposits this. And then on this one, my electrode comes in from the bottom and I deposit it and it melts this plate and it melts this plate, and that's what makes the connection. All right, so that's what's a fillet weld. Okay, this is strictly a shear type of weld. Okay, all the forces that go through this are shear related. Okay, whereas a groove weld could be a tensile effect if I'm pulling this way. Okay. All right, now there is another one that you'll come across from time to time. Typically we try to avoid these, but some cases it's required in maybe some seismic considerations where I have a little bit of a glare happening there. Sorry about that. Okay, and this is what we call a slot or a plug weld. Okay, and so what happens is that I make a plate and I put these holes or slots in it, and then back behind is another plate. Okay, it's acting back behind this thing, and basically I fill the holes with weld. Okay, and so then this is a huge area of contact, so you get significant increases in weld. Okay, and it helps to transmit a lot of the forces by shear, across these, what we call a lap joint, where one plate is laying on top of the other. Okay, and it's helpful when my dimensions of my weld are not large enough, or I can't establish, the length of these welds to support the given load. Okay, and so this is a way of picking up some extra capacity, assuming that I weld all the way around like this. Okay, now typically plug welds and slot welds are used in conjunction with other type of welds. Okay. All right. Now, one of the things that makes welding kind of interesting is there's a whole other language for how we declare our symbology on this. All right, so with welding, there's almost a special language that's developed, put on drawings in order to convey all of the information associated with this. And I'm going to show you the table where it's at. We're not going to spend a lot of time dealing with this either, but if you work in a fabrication shop, the drawings will show how things are constructed. Okay, and it basically points, to the location where the weld is to be applied. That's this arrow, okay, and that's the location where it's being connected at. Okay, the all around means that at that point I'm going to trace it all the way around the object and come around and make the same weld characteristic here. Okay, now in the events where I have multiple plates on this, maybe it's a double splice type of connector plate like this, and I decide I want to weld this and I want to weld this. Well, then I can call this out as basically a simple fillet weld connection. Let's say it's 3/16 of an inch. Okay, and then I can do a far side that has the same 3/16 of an inch. I can declare this weld on that connection with just that simple set of symbology. Okay, so the near side information is the critical part. Generally, that contains some facts like the size of the weld, and then the type of the weld is also shown up in there. Okay, and so I'm going to point you to table 8.2 in the manual. Okay, and this is the kind of, it's basically an anatomy of our welding characteristic, and so a lot of the information that comes out of here. So a fillet weld is basically characterized by a triangle. You saw me draw that in the picture. Okay, and then if I come and I look for the different types of groove welds, there's the square weld, notch weld, some sort of bevel where it's straight up and down on one side, so forth, so on. So all of this with just a couple of strokes of the pen, I can declare out what the weld type is, and whoever's constructing it then knows what they need to be doing, whether it's a fillet weld or whether it's some sort of internal, weld that requires some extra preparation. Okay. Now, the other term that shows up sometimes that you'll see is this little black flag guy, okay? And this is a symbol that means that this weld is to be done in the field, okay? Once you get the piece onto the job site, they're going to do the welding in position, okay? So I can't, whenever you see that, you've got to make sure that you have a qualified welder in the field. They've passed all of the AWS certifications, the quality control is in place. I mean, there's a lot of challenges whenever this little guy shows up. So, as a structural engineer and an inspector, you're wanting to kind of keep your eyes open for those guys. But again, there's a whole lot to it, but this is more of a kind of a reference for you to kind of look at. So I encourage you to kind of go through. There's a whole lot of lingo that goes into how we're doing this. I'll show you a couple of simple ones as we start to move on that. Okay. All right, so one example that we might have is maybe this is a column base plate. Okay, and so what we want to do is we want to specify a 3/8" fillet weld for a weld around the perimeter of a column. So I'm going to weld this plate. So maybe this is a PL 1 inch by 12 inch by 12 inch type of plate, and I want to specify a 3/8 weld to be able to establish that plate connection. Okay, now in this, the squiggly part would be my weld line, and so basically what we would do is we would say that, the 3/8, here's the character for the fillet, okay, and then basically, since I'm going all the way around this thing on this perimeter and coming back to the point that I started, because again, welding is a linear operation. It basically goes up and it just kind of continues all the way around, whether it's a man or a robot or whoever's doing the welding. Okay, and so this is the all-around symbol, and then those are the facts. And so this tells me everything I need to know about how to connect this plate to this section. Maybe this guy is, a W8 by 31 column or something. All that detail, that would be everything I need to know how to make that assembly in the shop. Okay. All right, and so if I look at it, that's basically, this is what's happening to this. This is now a cross-section of this, that here's my plate 1 by 12 by 12, and then this guy is my W8 by 31, and that becomes the assembly drawing for what would happen. Because typically we pre-weld the plates to the column so they don't have to do it in the field. I get a better connection, and I can just pick it up off the truck and set it in place when I go to set it. Okay. All right. Now, factors that are affecting the welds include the following. Okay. There's a lot of things that can play a role, but the three major ones involve the edge or the surface preparation, right? Typically metal, when you get it, is rusty, or it's got a little bit of oxidation on it. Okay, and all of that can interfere with your weld quality, can provide kind of a shield for that fusing process that we're looking at. Okay, almost always welding, we're looking to expose the bare metal, and we're going to remove the rust and the grime and all that kind of stuff. If it's an existing structure and it's painted, I've got to get the paint off before I weld, because again, that paint layer can provide a kind of an interference for the weld as well, that I can't get a real good bond, if you will, between the weld metal and the base metal. Okay. We also want to make sure that we get the appropriate process. For us, we're looking at kind of a TIG or a MIG type welding, or a submerged metal arc process. Okay, and that we choose the proper weld electrode to match the metal. For A992 and A36 and E70 electrodes, fine, but if you're working with a stainless or some sort of galvanized, I have to do something different. You'll have to spec the electrode a little bit differently. Again, that's beyond the scope of what it is that we're trying to do. Right now, once you get those factors down, and those are pretty easy to spec out and control, the last one is the one that's is a major issue, and that's controlling the heat. Okay, because again, we're heating this metal to a molten red almost liquid state on this. And so what happens is take an example that if I do a real long weld on a plate that's very, very thin, and this line comes in, liquid red hot on this thing, when it cools, what's going to happen is this thing's going to start to contract, and it will actually curl or warp the plate. Okay, and that introduces stresses, and you start getting alignment issues, and so forth and so on. Okay, so being able to control the heat of this is a major issue. Now, one way I could do it, I could go 4 inches at a time and then let it cool off, then go 4 more inches and let it off and so on. Or I could do something called a stitch weld, where I weld a little bit, leave a little bit of a gap, weld a little bit more, leave a little bit of a gap, and so forth and so on. But it requires a whole lot more length to do it. But this isn't totally uncommon to help control this warping effect. This is called a stitch weld that you'll encounter. Okay, but it's bounded by all the same rules of fillet welds and groove welds when I go and do them. It's just a type of, it's basically the pattern that it goes for a length. It's on, then off, then on, then off, then on, then off, so forth. Okay, but it's this warping and this curling that, when you heat something and it kind of gets out of, you have everything nice and framed up square as could be, and then you weld on it, and all of a sudden now it's warped and out of alignment, and that's not necessarily a good thing. Okay, all right, so that's kind of the basics of welding. Let's get into a little bit of some of the specifications that AISC uses for this. Okay. All right, so the design criteria for the weld are all found in Section J of the specification. In fact, it's Section J2. If you recall, Section J also contained the specifications for the bolts. Okay, so in the 15th edition, we're looking at 16.1-116. And there are several things that we have to kind of look at. Okay, the first one is that for any setup that you have, there is a minimum weld size that is allowed. Okay, because what we don't want to have happen is you have a really big plate like this, and I put a little bitty weld on that thing. Okay, if this is a very large dimension, in fact, as part of the heating process, to make a good weld, you have to heat the base metal to a certain amount prior to getting the weld on there in order to be able to make a good connection. Because I put something really, really hot onto something really, really cold, I could get microfractures on this thing, or it just doesn't penetrate in as well as it should. Okay, that it cools it off too fast, and this becomes a very weak weld. So there's a minimum weld size that's going to dictate that I have to go to a certain point in order to be able to establish that. Now, often we like to do this, if the plates are small, I can do this in one pass. But if the plates become really, really big, what happens is sometimes I'm forced to do multiple passes and start to kind of build this thing up, through multiple passes. And every pass you make takes time. And as they say, time is money. So we try to size a weld so that I can do it in a single pass, maybe two. But to get into these larger weld sizes of, inch, larger than an inch or inch and a half of weld, not only do you have a major, major problem with heat, but I also have an issue with the time and the cost of doing these multiple passes, because the further I go out, the more passes that it takes to add on to build this thing up. Okay, all right. So that's always a consideration. You'll find that located in the tables J2.1 through 2.4. Fillet welds are in 2.4. Right, so let me show you what that table looks like. Okay, and so for us, again, since we're predominantly worried about the minimum size of fillet welds, we'll be looking at J2.4, and you can see that for up to 1/4 inch, the minimum size is 1/8. Up to between 1/4 and 1/2, the minimum size is 3/16. You can see that for the plate sizes, it gets a little bit larger as you go up. And so this will dictate the minimum weld size. And sometimes you get into cases where you're trying to connect two pieces of plate where this minimum, can't be achieved, because you're on the other side of what we're going to show you. There's also a maximum that we have to compare. And I'll show you some details about that as well. Okay, over on the other tables, 2 and 3, those are where you can find information about the groove welds. Again, kind of aside from the process that we're dealing with, okay, and what your dimensions are accordingly. Okay, and most of the often you're worried about this throat thickness, and so I should leave that as an exercise for you guys to look at as well. Okay. All right. Okay. The available strength table in this is table J2.5. It's the next table, and this is where kind of the meat of all of our information is contained, and that's this table here. Okay, and you can see that in this, I have all sorts of different types of directions of welds and different types of welds. Okay, and so I have, tension normal to the weld axis, compression normal to the weld axis, and it kind of tells you all the factors that you need to know. It gives you a phi factor, it gives you the nominal stress associated with the base metal, and then it gives you the areas associated with, with these calculations that we're going to look at. And I'll explain that here in a second. The next is our partial penetration groove welds. And then on the last page, if you flip it over on here, we're looking at fillet welds, including fillets and holes and slots, okay? These shear connectors, and everything that we want is right here, okay? And so you can see that our phi is 0.75, corresponds to a rupture state. The nominal stress in the weld is 0.6 times the electrode strength, okay? And then the effective areas are outlined by the details that I'll explain here in just a second, okay? So a lot of what we're doing is back on these section J2 and all of the reading. There's a lot of just little details that go into this whole process, if you will. Okay, all right. But the major factors that come out of that table are that we need the electrode strength and I need phi to be able to do that. Okay, all right. Now, the actual strength equations come out of J2.4. And what they say is that for every weld, there are two sides. Okay, there's the side of the weld that connects to the base metal, the plates that are being welded, and then there's the weld itself. And so you've got to figure out, is my weld large enough to sustain the loads? And then is my base metal sufficient to be able to grab onto the weld and keep from ripping the weld out as a unit? Okay, and you have to do that on both sides. All right, so if we look, and we'll kind of define these different properties here. Okay, so the FW, that's that FWE that came out of that table J2.5 that I just showed you. The effective weld area is basically the throat of the weld multiplied by the length of the weld, okay, for the weld metal. For the base metal, it's the FY. FBM is the FY of the base metal, and then ABM is the cross-sectional area of the part that's being connected. Okay, so that's sometimes a little less than intuitive on, ripping the metal exactly at the location of the weld. Okay, all right. So, and again, we'll come back to this here in just a second. The other criteria that we have to look at then is the maximums. Okay, and this is our maximum fillet weld size. Okay, it's located in J2.2b, and it's not real obvious, but if you read the text, this is what you kind of deduce in picture form. Okay, for plates that are being connected that are less than 1/4 of an inch thick, the maximum weld that I'm allowed to use is 1/4 of an inch. I can go all the way up to the top. Okay, however, for welds that are larger than that, you have to take the thickness of the smaller part and subtract 1/16 of an inch. Okay, and you have to check that for both sides, right? So if this one's over 1/4 and this one's under 1/4, you have to figure out which one controls as you start to calculate this AMAX characteristic. Because again, the possible failure locations are I fail the base metal here, I fail the weld itself across the weld, or I fail the base metal there. All of those will break this connection. And so you have to check the base metal on both sides and the weld himself. Imagine the base metal failure as being a way of, I'm just going to rip this metal either at the interface of the weld or back a little bit on there. Because again, as you're heating this, you're recrystallizing or reforming the structure, at the chemical level almost for the base metal itself. Okay, and so we're looking at tearing chunks of this off, and that's why we're using that cross-sectional area, which would be that dimension coming down that way. All right, so you got to kind of play both sides of this. Okay. All right, now the other parameter that's important to us has to do with the effective weld areas. That's that AWE. That's our AWE calculation, or the ABM that we're going to deal with. And so, again, coming out of the words of this for the groove weld section, okay, we're going to define a parameter known as the effective throat of the weld. Okay, and that has to do with the way that this weld will fail under load. Okay, so for groove welds, if I have two plates and one plate T1 is smaller than T2, in this case, the effective throat of a groove weld is equal to the smaller. And that should make sense, right? I can't have a weld that's T2 wide if I only have T1 in height. Okay, so that should be pretty effective. Okay, so that's a kind of a bevel groove weld. Okay, and then here's what we have is a penetration groove weld, in which I've coped the ends of this thing, and then I'm going to weld this, and then I have to flip the plate over and I have to weld the other side. So this is a two-step process to get this. Okay, and so for our weld, if T1 is equal to T2, then the effective throat is equal to T1, or technically T2. So that should be no major surprise. Okay, the one that's a little bit different is this last guy, okay, and this is called a partial penetration groove weld, okay, and so what we have is we have kind of a beveled edge, and then it comes in, and then kind of this flush, flat connection here, okay, so there's no connection on the bottom side of this, but this is, it kind of solves the problem that you had here and having to flip the part over that I can do this weld, okay, and then the angle of the bevels has to be between 45 and 60 degrees. On this. If you get any flatter than that or get any steeper than that, then you have some issues. But again, what you're worried about in all of these is that this is an interior weld, and you can get a spot that doesn't get any weld if this thing doesn't form correctly. Okay, so what they do is they declare the depth of the bevel as this variable d, and then the effective throat is assumed to be d minus 1/8 of an inch. Okay, and this 1/8 of an inch is because, again, we don't know what's going on the backside, and this one, unlike the other case that we showed you earlier, there's no way to check, right? Because this is a flush connection on the back that even if you flipped it over, you wouldn't be able to see in there. So short of doing some sort of ultrasonic testing or, you know, it's next to impossible to know. So that's why they're penalizing you 1/8 of an inch on the effective throat on a partial penetration, you know, V-joint or bevel groove weld that we have on there. So that's the groove welds and the characteristics of the effective throat. For the fillet welds, thankfully, is a whole lot simpler. All right, so my fillet weld, we showed that as kind of being a triangular region on this thing. Okay, we call the side of the triangle is the leg size. And so if you see a 1/4 inch weld, that's what they're talking about, is the leg size is a 1/4 inch. However, for strength, when you're checking the weld, on this, the shortest distance that will shear or fail is this guy that comes right across here and goes 90 degrees to that line. Okay, now typically we assume that these guys are 45 degrees, right? And so the shortest distance here, that's TE. So with a little bit of trigonometry on this, I can say that the TE is 0.707 times A. All this is the sine of 45 degrees. Okay, and that will get you to be able to, because the TE is the hypotenuse of a triangle that involves, you know, is the side of a triangle that involves A as the hypotenuse, all right? Okay, so if I have TE, then the area of weld that has to fail in order to fail the weld himself then is TE times whatever length this weld has. So a lot of times as we're detailing stuff, we don't know this guy right off the bat until we're done with the detailing. So a lot of times what we'll do is we'll declare welds in terms of, you know, a kip per inch of length. So, you know, if I have, you know, 4 kips per inch of capacity and my load is 10 kips, I know I need 2.5 inches of weld length in order to be able to support that load. Okay, and that's just 10 divided by 4 is all you're doing. Okay, and that's kips per inch. So a lot of times we work in these normalized weld per inches, and then we spec the length out on the drawings as we start to do it. Okay. So if we take our strength calculations and we plug in all of our parts on this, when we check the weld metal, it's basically going to be equal to then 0.75. So this first term on both of these, that's phi. Okay, it's going to be the effective throat, okay, and then multiplied by 0.6 times FEXX. And then the base metal, we're going to take as 0.75 times T, and then it's 0.6 times FU. We'll get us that calculation as well. Sometimes we'll take this as FY also. Okay, it kind of depends on your application. But those are the way that you start to calculate the strength for a fillet weld. Okay. All right, and with that, I think we will go ahead and stop with our basic welding primer for now. Okay, in the video that comes immediately after this one, we'll have a couple of example problems. I'll kind of walk you through how we can decide some things, but hopefully that gives you kind of an understanding of a lot of the different factors and the different terms associated with welding. Again, remember that, you know, there's a minimum size of weld, a maximum size of weld that has to be obeyed, and the weld that you actually choose has to be between those two numbers. And if it's not possible, then you have a real issue on your hands, and so you've got to be careful to be able to work that out. Okay, so, and then as always, we need to be able to check both the weld and the metal that's being connected to the weld in order to ensure that the weld calculation is is sustainable. Okay. Again, welding is a very complex process. Okay. It's the average person can't just pick up a welding gun and go out and start welding and do it with any sort of competence. It takes, practice and training, and then you have to be qualified and meet certain standards and certifications to be able to weld in certain jobs. And then even within a job, there are certain types of connections that can only be made by certain people. And as the welding gets harder and more difficult, certification becomes more and more critical. Then, of course, the cost for the welder to do the work becomes more and more critical because he's got an expertise. So lots of things that go into this. Bolts are so much easier. Okay, you pre-drill a hole, throw a bolt in, and you're good. But welds, there's a lot of, do I do it in the shop? Do I do it in the field? Or what have you? So like I say, hopefully this gets you kind of a taste of the different welds basics at this way, at least for groove welds and for fillet welds. And then, like I said, in the next video, we'll do some examples involving fillet welds and some other considerations with us there. So anyway, I hope this has been pretty clear for you. As always, if you'll like the video or leave us some comments on what worked, what didn't, we would greatly appreciate the feedback. And then, as always, please be sure to subscribe to the channel. And I will see you momentarily in the next video. Thanks.